Hello everyone, in the last video we have seen the identity and the various operations which we perform in the Boolean algebra. In this video we will be describing more about De Morgan law. So what is De Morgan law? So basically De Morgan law is the fundamental rule that describes the negotiation of logical expression which is involving and or popularly known as conjugation or disjunction or. There are two main De Morgan rule or you can say De Morgan law. So let's start with the first law. So first law is De first De Morgan's first law, and basically this law is for AND operation. So what does this law say? Suppose we have two input A and they are in the AND operation A dot B, and it is the negotiation, means it is just the not of the AND operation, then it will be equivalent to A naught plus B naught. So if we make a circuit diagram for this, so what it basically mean to say? So it is basically saying that if we have two input and if it is connected to AND gate, if suppose this is A, this is B, so its not will be our output. Suppose this is the circuit this side, so it will be equivalent to A not B not, and it will be further connected and it will be connected to OR gate. Oh sorry, OR gate, not, yep. So what does De Morgan first law say? That the product of A and B is equal to the sum of the negotiation or negotiation not of A and not of B. We will also prove it with the truth table. So let's move to the truth table for De Morgan first law and let's check whether it hold true or not. So let's start making the truth table. First will be our A and B input. Okay. Now second thing we want is A and B. Now third thing we want is A dot B not, and fourth thing we want is A naught, fifth thing we want is B naught, and the sixth thing we want is A naught plus B naught. So let's slightly move it up and let's draw a line here to separate it. I know my drawing is not that good, but I hope it is easier for you to understand. So, or slightly move up. Yep. So first thing I will write all the possible combination. So since we are having two input, so 0 0 0 1 1 0 and 1 1. we have to check whether this is equal to this or not. If this is equal to this, then our De Morgan first law hold true. So first we will perform the AND operation. 0 into 0 it is 0, 0 into 1 it is 0, 1 into 0 is 0, 1 into 1 what is 1. Now we are means applying not over here, so it is equal to 0 not 1, 0 not 1, 0 not 1 and 1 not 0. Now this is A naught. So wherever it is 0 it will become 1 and wherever it is 1 it will become 0. Same with the B naught. So wherever it is 0 it will become 1 and wherever it is 1 it will become 0. Now we will be performing OR operation between A naught and B naught. So 1 1 it will be equal to 1, 1 0 it will be equal to 1, 0 1 it will be equal to 1, 0 0 it will be equal to 0. So from here we can conclude that this is equal to this. So our De Morgan first law hold true. So now let's move to De Morgan's second law. So let's see De Morgan. There is a space between D and Morgan. De Morgan's second law. So this law is basically for OR operation. So let's slightly move it up and see what's our De Morgan second law say. So according to De Morgan, A or B naught is equal to A naught and B naught. Basically it is saying that negation of sum of OR operation is equal to product of negation of A and negation of B. So let's first do you want to make it a circuit diagram? So let's make it. So what will be this side circuit looking like? It is a OR gate and basically it is NOR A B. It should be equal to A not B not and it will be attached to AND. Okay. Now let's make truth table so that we can prove whether De Morgan's second law is true or not. Or let's see. So same as previous experiment like what we did, we will be making truth table A, B, A plus B and then A plus B bar and we want A bar, we want B bar and we want A dot B bar, right? So now let's see. We have to check whether this is equal to this or not. So let me draw some separator. Here it is, here it is. So now writing all the possible combination, it will be 0 0, it will be 0 1 1 0 and 1 1. Let's start filling all other table. So 0 0 it will be 0 0 1 it will be 1 1 0 it will be 1 it will be 1. What will be negation of this? So it will be 1 0 0 and 0. Now A bar. What will be A bar? It will be 1, 1, 0, 0. Here it will be 1, 0, 1, 0. Now A, we have to perform AND operation between two. So 1 into 1, it will be 1, it will be 0, it will be 0, it will be 0. So from here we can see that A plus B bar equal to A bar dot B bar. So from here we can say our De Morgan's second law also hold true. So now let's see the application of De Morgan law. But before moving to the De Morgan law, I want to just make you some awareness regarding the notation. Like we are currently mentioning a bar, but you may find in some book it might be written as a dash. So this is the same thing. Suppose a plus b bar is there. So in some book it might be written as a plus b, it will be in bracket and this bar sign will be there, dash sign will be there, so it is the same thing. Now let's look at the application of De Morgan's law. Son of De Morgan law. So I think I have written the De Morgan's law here, so do remember this. It is very useful law and it will be used in many places. So IMP, again I will write it here. This is also IMP. So do remember it. Now let's move further and discuss regarding application of De Morgan's law. So first most application which we often used is simplifying fine Boolean expression. As I told you about, we will be simplifying this circuit. So before simplifying the circuit, we have to simplify its expression. Then only we can simplify the circuit, right? So we will be using this De Morgan law for simplification of the circuit. Second, we will be also using it into logic circuit design. Basically it is same. If we are able to minimize the circuit expression, then we can create the circuit design also. And all other are same, like optimizing the circuit and time complexity management, like that. So we can use them. Now before moving further, so let's see some example. Like we are simplifying Boolean expression. Although I will be covering it in more deep, but for just the simple information, let's do a simple circuit simplification. Okay, so let's start with some example and some simple circuit. Suppose we have a circuit A plus B bar. Although this is very simplified, so can we change its form? Yeah, we can do it by using De Morgan's second law. Right? A plus B bar equal to what? A bar dot B bar. So this circuit can be represented in the form of this also. Now let's move and see some complex, slightly complex. It is not that much complex, but it is complex. So second example. So suppose we have an algebraic Boolean expression A bar dot B plus C bar plus D. and there is a whole bar here. Now you might be thinking that we have not seen anything for the 4 input. We have just seen it for the 2 input. So how we will be utilizing De Morgan's law here? So from here you can see that this is one expression, this is a separate expression, and we have a or sign and a bar sign. So can we write it like this, that G1 equal to A bar dot B and G2 equal to C bar plus D? Can we write it like this? So our further equation will become G1 plus G2 का whole bar, right? So now here we can see it is similar to our De Morgan's second law. So we will be utilizing De Morgan's second law here, or yep, De Morgan's second law, which is basically for the OR operation. So here what it will become, G1 plus G bar. So it will be equivalence to G1 bar dot G2 bar, right? Now we can actually write in this form, just replace it like that. A bar dot B का whole bar dot C bar plus D का whole bar. Can we write it like this? Yup, definitely. Now see, can we simplify it further? Definitely we can simplify it further, right? Like if we go and see, we are having De Morgan first law as A dot B bar equal to A bar plus B bar, right? So can we simplify it like this? A dot B bar, okay, का whole bar is there already. So it is equivalence to A bar, okay, का bar plus B bar. If I am not correct, if I am not wrong, yep. And second it will be C bar का bar dot D bar, right? So here we are utilizing both second law as well as first law, right? Now from yesterday understanding, we can say a bar of bar will neglect each other and we will be getting A plus B bar, and second it will be C dot D bar, right? So from here we have arrived to this position. Simply from OR operations we are coming to the AND operation here, and it is more simplified form. So from here we can say that we can change a circuit from a form to second, it's we can change or we can simplify it into other form. So we will see more of the simplification process. I know this was slightly easier because it is just 4 variable, but there might be 4 or 5 or 6 variable next time, so we will be see accordingly. So in the next video we will be describing about circuit simplification process. Simplification process. So if you have liked, means if you have gained any knowledge from this video, do like the video. If you have got nothing from this video, you can dislike the video. And if you have any question, so you can just post it in the comment. I can answer it directly there. So I will see you in next video where we will be describing more about circuit simplification process. Thank you.